Hi everyone, this video is for section 4.4, the fundamental theorem of algebra. What I'm going to attempt to do is tell you some of the theorems behind the problems that we're going to be trying tomorrow in class in order to save us time so that we can do sections 4.4 and 4.5a. So the fundamental theorem of algebra states that if a polynomial has degree n, as long as n is greater than or equal to 1, then p, the polynomial, has at least one zero. That is, the equation p of x equals 0 has at least one solution. It's important to note that the 0 of p, and consequently the solution of p of x equals 0, may be a non-real complex number. And the complex number, if you recall, is of the form a plus bi. So it could have complex zeros, it could have real zeros, it could have a combination of the two. Next, the linear factors theorem states that given the polynomial p of x equals a sub n x to the n, so on and so forth, till we have a constant, where the degree again is at least 1 and the leading coefficient is non-zero, then p can be factored into these linear factors. So you have some leading coefficient and you have factors x minus c sub 1, x minus c sub 2, all the way down to x minus c sub n, where these c's are constants, but again, possibly non-real complex constants. And they're not necessarily distinct. So some of those can be the same. So this could be x minus 1, and so on and so forth. In other words, an nth degree polynomial can be factored as a product of n linear factors. The multiplicity of zeros will tell us a lot about the graph. Multiplicity simply refers to when we have those factors x minus c, depending on how many times it appears, where it appears at least one time, then the multiplicity, we call k the multiplicity of that zero, c, and we see that multiplicity right here in x minus c to the k. So if we had x, let's say, plus 3 to the second, then we would say the 0 is negative 3, and it has multiplicity 2. Now this has an impact on the graph of the polynomial. So what does that mean? If c is a real zero of multiplicity k of polynomial p, or another way to state that equivalently is x minus c to the k is a factor of p, then the graph of p will touch the x-axis at c0, and it will cross the x-axis if k is odd. So if the multiplicity is 3, 5, 7, so forth, or 1, then it's going to cross through the x-axis. And if it is, if k is even, then it's going to stay on the same side of the axis, like it's going to touch or bounce, however you want to call it. Furthermore, if k is greater than 1, then the graph of p will flatten out. So for instance, if we were to look at, let's say, a simple polynomial, let's call it f of x equal to 3 times x minus 1 squared. Now that 3 is just a multiplying factor. It's going to stretch our graph out. It will not have an impact on where the 0 is. If you look at that factor right there, it tells us that x equals 1 is our 0. Notice it has multiplicity 2, which is even, and that means that when we graph this polynomial, it's going to do something like this. It's going to touch right there at 1, and then it will sort of bounce and continue onward. So it's not crossing through the axis there. The same would have happened if I put a negative, which just would mean that it would be upside down, but again, it wouldn't cross the x-axis at 1, it would sort of just touch it. Last but not least, we have the conjugate roots theorem. This theorem states that if you let the polynomial be a polynomial with only real coefficients, well, if the complex number a plus bi is a 0 of p, then so is the complex number a minus bi. In other words, they're conjugate roots. So our complex roots will travel in pairs. If we have a plus bi as a 0, then by necessity, so is a minus bi. That means by extension that if x minus a plus bi is a factor of p, then so is x minus a minus bi. Okay, we'll do one problem together, but we'll save most of it for the class. And so if we look at this example right here, let f of x equal this polynomial that's already in factored form, what do we know about the graph of f of x? And what we know is we can tell its end behavior because we know the degree and we know the sign of the leading coefficient. And so what is the degree of this polynomial? Well, let's take a look. We have a 1 here, right? A 2 here, and a 2 here. So this polynomial is degree 5. We can simply add those up, the variable terms, right? Then we see out front here we have just a positive 1 since we don't see anything. And so our leading coefficient is positive. So we've got a degree 5 and a positive leading coefficient. We are expecting something with end behavior like so, right? Down, up, like a positive cubic function. So odd and positive, we're expecting this. What else do we know? We know that the zeros of this function are going to be x equals -2, x equals -1, x equals 3. Now this 0, x equals -2, has multiplicity 1, which means at that particular 0, the graph is not going to flatten out. At x equals -1, we see once again we have multiplicity 2 here, which is a little different. So we're going to see a flattening out. And also we are going to touch the x-axis and then continue either upward or downward from there. At x equals 3, we see multiplicity 2. So we see the same thing here, multiplicity 2. And again, we're going to flatten out. And we're going to touch the x-axis. We're not going to cross it. And that's it.